today is more important as a class. I will skip some of the things in the slide because you'll be hearing them again in the interest of time in other classes. It's about essentially the foundations about a learning problem. So it's kind of high level and therefore a little bit difficult. It's rather abstract, but some of the concepts, in particular ideas of generalization error and predictivity, are very fundamental to learning. If you ever want to start a hedge fund and have $1 billion to bet on a prediction of your learning algorithm about what the market will do tomorrow, you better listen today. Okay? Because you have to have guarantees that the algorithm you're using can generalize. And I'll explain what that means. Okay. Now, in general, the kind of learning we speak about is not about explaining the data, but it's really about predicting. And typically this is from small training sets of high-dimensional data. High-dimensional means that your X variables have large dimensions. Now, in terms of classical statistics, as it used to be until 15 years ago or so, high dimensions meant probably anything above dimension 2. This day is different. For instance, we speak about learning algorithms on images where the dimensionality is 200 by 200, several thousand components in a vector. So small, it means small relative to dimensionality. High dimensional spaces are very, very empty. Think about it. And they're very different from what we are accustomed to think when we are dealing with 2 or even 3 dimensions. So small, when you are working in a dimensionality a few thousand, could be hundreds of thousands of data. That's small. Okay, this is as a background, but the reason for the class today is to give you the big picture, the rationale for doing things like we'll do in the course. For instance, today I'll give a pretty fundamental justification for the use of regularization in learning algorithms. And you will see much more about the regularization techniques in details over the next several classes. It's also a good time to check how much you understand. You may need or not math camp next. For instance, I will speak about convergence in probability and concepts like this. And of course, the main reason for this is that learning is really now part of mainstream mathematics. And something that works in practice. So we'll speak about the mathematical, almost philosophical foundations of it. First of all, there are many learning problems, not just one. The one we'll speak about is really supervised learning, today anyway. And it's really at the basis of the course. We'll deal over the course with some of the other ones, like semi-supervised, unsupervised, online, transductive, active learning. Reinforcement learning is quite important in biology. But today we'll speak about supervised learning. And in a sense, that's the one which is most clearly and cleanly defined is the basic one. There are some reasons that I will mention towards the end of the course in the last few classes why it could be a basic building block for everything else, even in the context of biology. The idea of implicit supervision. Okay, so statistical learning, this is what the class is about. It's, we need statistical formulations in terms of probabilities to deal with noise. It's always present in the data. And we'll see why regularization is a general framework to design different algorithms, so a class of algorithms that can deal with the noise and the predictivity problem in learning. So again, oops. Some problems here. Can I bypass recording?
Okay.
How do I do that? There is a box between the projector and...
It's connection issue.
Sorry?
It's connection issue. You got it right now.
Yeah, it came back.
Came back.
Okay. Should we try?
Yeah, continue on and I'll
Okay.
see what the issue is.
Yeah. Okay. So,
There it is. Okay.
thank you. So this is just what I'll do. So instead of going through this, let's see it coming. So what I want to do today is really part 1 and part 2. Part 3, I will give you a brief introduction because you will see the algorithms in the several next classes. But you have the slides on the web, you can see part 3 there. So, first, definitions and notation. We call the training set, so the n pairs of x, the input, y, the output. We call this training set S subscript n. It has n element, and a learning algorithm is using those data Sn, and based on it, I'm shortening Sn to S, is choosing a function that depends on the training set that provides for each x a y. And the x, of course, in general, is not one of the xi. So, of course, you cannot learn everything. There must be a relation between input and output. In particular, you assume that each input-output pair is drawn from a distribution of pairs, x and y, according to a law, a probability distribution, a distribution mu, which you assume exists, but we don't know in general. Okay? When we're trying to learn, we don't know what mu is. And under relatively general condition, but it's not always true, so the mu always exists, the distribution, the probability p of xy, which is the integral of the distribution, exists most of the time. You know, it does not exist if it's defined, for instance, on a submanifold of this Z on a lower dimensionality. But let's assume it exists, and then I can represent a px comma y in terms of the conditional probability of p of y given x. So I want this, for learning to be possible, to depend on x. For instance, if I ask you, suppose I give you a telephone book. They don't used to exist. They used to exist, right? Telephone book. So telephone book is, you know, you're mapping a name like Tomaso, Poggio, that's X, to a telephone number, whatever. You can find it. X, Y. Now, I ask you, I give you the old telephone book. I take some of it away. I don't give it to you. That's the test set. So you can use all I give you to train, to learn an algorithm. Can you learn this mapping? Meaning, when I test you, I give you a name which is not in what I gave you. Can you tell me the number? What is the answer? No. There is really, in general, there should be no dependence of y on x. Okay, it's random, impossible to learn. So in order for learning to be possible, there must be some dependence. So py comma x cannot be a constant relative to x. Also assuming, as I said, that I'm sampling in a way that is IID, identical and independently. Independently can be relaxed. Identical is very important. Okay, that's a setup. And so there must be this relation between this dependence of y from x. I'm speaking of this in a statistical sense with the probability. If it's completely deterministic, which is unlikely, then of course that's a special case of this probability. But in general, there will be some noise in the measurements of y. The underlying process itself could be noisy. There could be incompleteness in the available information. That's y probability. You can see this here. Suppose that I have a p of y given x, which is as above. I have a prior p of x, this is the distribution of x. And that's the true functions, which I don't know, but the samples have been taken from it, for instance, in this way. So this reflects the prior probability. And they could also be taken with discretization errors. So let me make an example of a deterministic case affected by noise. Suppose that I have a spring and some particle here, and the force which this mass feels depends from the displacement. Okay, that's the Hooke's law, linear spring. Okay, then what is P of f given x? This is the y, this is the input. This will be, it's a deterministic, no noise so far, so it will be a delta of f minus ax. Okay? This means that if I have here the force, the y, it will be something like this. X is here. The force depends linearly on the displacement x. Okay. Now, suppose I have noise either in the measurements, perhaps in the measurements, or because Hooke's laws does not hold exactly. So suppose this noise is Gaussian, then what is the probability? Well, be something like a Gaussian centered in f minus a of x with some sigma squared that depends on the autocorrelation of n, the power. And so the plot in this case would be something like this. Is that clear? Okay. Now, the key property we want from a learning algorithm is to be predictive. So given a new x, to predict a y which is close to the true y most of the time. And in order to define predictivity, let me introduce the concept of generalization. First of all, however, I have to define how I measure errors, because I spoke about, if you predict, means I have to measure how well you predict. So we have to introduce a loss function that determines how much we pay by predicting f of x when the true prediction is y. Okay? Intuitively, if f of x is equal to y, my price would be, the cost would be 0. So first of all, the simplest loss function that I can use is maybe not the most intuitive, but the easiest to handle mathematically is the square loss. And we'll deal a lot with that. But there are other ones. Instead of the square, I can use the absolute value. All of this is pretty arbitrary. In some problems, some is more reasonable than others. There is also this one, is the epsilon insensitive loss of Vapnik, which is, so this is the square loss. This is x, and this is v, and this is the loss, f of x, the error. The absolute value would be somewhat similar. The Vapnik's epsilon insensitive loss is something like this. So essentially, if the error is small, you don't pay anything, and then you pay in a way that increase linearly with the size of the loss. This symbol here is a plus, is the positive part of the function inside. So it's the max between 0 and the quantity inside the parentheses. Okay, this is for regression when f of x minus y, y is a real number, f of x is a real number. There is also the case of classification when y is either 0 or 1, binary classification. And then there are analogous definition. For instance, the natural one is that if you predict 1 when the true y is 0, then you should pay fully. If you predict 1 when y is 1, you should not pay anything. So that loss function, which is yf here, will be something like this. If you have the same sign, you don't pay. If your sign, the sign of prediction is wrong, then you pay. But again, I can use also the square loss, which in this case can be written in this way. You can check this when y is plus 1 or minus 1. So this is equal to f of x minus y square. And one which is mathematically more tractable is similar to the step function, but is this one, which I show in the next slide. So they're all together. Let's see, can we see this? Kind of. This is really bad. You see, let's see, this is the 0-1 loss. This, let's see. Yeah, this is the hinge loss, Vapnik's hinge loss. Actually, it should be go here. I don't even see the. Okay. Hope you have the slides. Yes.
For the hinge loss?
Yeah.
Why does it go to 0 at 1 instead of 0?
Well, that's the definition. You pay not very much if you predict something which is right but not very right. It's surprisingly in practice, there are always some, for each problem, specific problem, one of the loss functions may be better than another, also in terms of training an algorithm. But it's not obvious which one a priori. And even for classification, the square loss, which looks kind of wrong, because the square loss you pay even if you are right, but even the square loss, even for classification, works pretty well in general, so across different problems. That's just an empirical remark. Okay, so now we have define these losses. You can look at it again, but for now, just let's keep in mind this one when I speak of loss, because it's the simplest to deal with. So now we can introduce the get into predictivity, generalization, first I have to define this, which is called the expected error. This is the error I expect to make in the future. You know, if I would know the full probability distribution, I don't, but then this is the error I expect over the probability distribution. If I would know the probability distribution, given my loss, I could compute this. If I am the hedge fund, I could find out this expected. How much is the error I expect in average, in expectation to make tomorrow? And then decide whether I want to bet $1 billion or not. Okay. The problem is that I don't know the probability distribution. So, again, just a reminder of what we have here. We have the probability distribution, which I don't know. I have the training set, which I know. There is a loss function, which I know. There is this quantity, which is the empirical error. So this is, could be, ideally, a proxy for the expected error, which I cannot compute because I don't know this P of X or Y. This one says, well, let's compute the average over the data I have. Okay? Superficially, it seems that if I would have infinite data, this should converge to the expected error. So the more data I have, the more this empirical risk, superficially, is not so simple, should be a good proxy for the expected error. So let me skip this. You have it in the slides. I assume you have some understanding of what convergence in probability means. We'll see this on Wednesday. Where's Charlie? Anyway, yeah. You'll do that, right? Charlie?
Yes.
Where's Charlie? Ah, so you will do that or not?
Yeah, sure.
Huh?
Yeah.
Okay, good. So I can skip all of this, right? I'll say something that follows from this one. No, I think Charlie will do that, right, Charlie? Good. So this is really the issue. I have this empirical error which I can compute. I have the expected error I cannot compute when when I have to learn from a given training set. So a measure of the difference between the expected and the empirical is called generalization error. The way you read that is that the probability, you'd like the probability of the empirical error to be within epsilon of the expected error. This probability should be large, very close to 1. For certain n that you have, number of training data. Now, you cannot compute this, but we can look from the theory whether a certain algorithm has this property or not. So if you know that in theory this algorithm has this property, and ideally you know this, how it depends on n, so the convergence rate, this is what Charlie will speak about. Then you have a guarantee that your proxy is good. You know how good it is. It's within epsilon with probability 1 minus delta. And that's the basis of whether I can decide to bet the 1 billion or not. Okay? So you want to have a lot of learning theory of the foundational part is really to say, you know, these are the important quantity. If I can have convergence rate of the generalization error, so how quickly the empirical error converges to the expected error, then I know that my algorithm or class of algorithm generalizes, and I can use the empirical error as a proxy for deciding how good my prediction is likely to be, is going to be. Okay, so that's, in a sense, the key part of the class. But there are obvious questions at this point. How we go from this notion to algorithms that actually work. And the first class of algorithms that comes to mind is, of course, algorithm where I take the empirical error, the error I make on the training set, and I choose my function in such a way that it minimizes that error on the training set. Is this a good strategy or not? How? Okay. So here are where the real results come. Let's first get rid, I think this concept of consistency is very important for classical statistics. I don't think it's very important in practice, but let's just get quickly through it. Consistency means that given an infinite, an arbitrarily large number of data, you can do the best. And there are several consistent algorithms. But let me go to the real issues. So let me introduce this idea that the learning algorithm is based on the data set, is choosing a function, you know, f subscript s, depends on the training set s. But where does these functions come from? Can they be any function? As we'll see, this is a key part of learning. And we'll see later that, in fact, which hypothesis space you choose, which function space, this is the bag of functions from which your algorithm will choose, depends on the amount of data you have. So, for instance, this is the most obvious class of algorithms that one can think about. I tried to minimize the empirical error. So the error on the training set. Question is, over which space of function do I look for finding the minimum, the best one? So repeating again, that's the expected loss. This is the empirical error, which I'm trying to minimize. Question is over which hypothesis space. And okay, and I want to choose H in such a way that when I do the minimization, what I find is a function that has a small generalization error. Okay? So you see already the key part in this class of algorithms that are called empirical risk minimization is H, how I restrict the optimization in such a way that the solution I find, the minimizer, generalizes. Now, in addition to this property of generalization, another one property which could be important is what is called stability. So stability is very important in many problems in mathematics and physics. Is the idea here that if you change a little bit your training set, the solution your algorithm finds should not change very much. Otherwise, you are in trouble. For instance, suppose the algorithm to predict the stock market will depend on data I get from the past. For instance, the closing of today of the S&P. At 4 p.m. the market closes. And if you look at it carefully, in the last few minutes, there are always a lot of fluctuations. And whether it closes at exactly this number or a few points higher or below, it's really very arbitrary. It's when various market mechanisms and the clock strikes 4 and so on. So, suppose you have you change this by a couple of points in your data that you feed in your algorithms, and the prediction it gives you tomorrow comes from buy to sell. That would be not very trustworthy, right? So you need this property of stability, as much as you need generalization. And now let me open a small parenthesis here. It's about well-posed problems and ill-posed. I mentioned that last class, but let me repeat. A problem is well-posed when the solution exists, it's unique, and this is the stability part. And usually that's the one which is difficult to guarantee. Okay? The other ones are a question of redefining the problem often. So, in a sense, learning is the prototypical example of an ill-posed problem. I have a function, I sample it, and that's the direct problem. The inverse problem is from the samples, pairs of xi, yi, I would like to reconstruct the function. That's clearly, just by itself, if I don't have other restriction, is ill-posed. The solution may exist but not be unique and almost certainly not be stable. in a sense, learning is the inverse of sampling as a problem. So it's kind of almost intuitive that it's ill-posed. Okay, so close this parenthesis. Let me go back to this class of algorithms. So the argument we're looking at to minimize the empirical error, find the function that minimizes the empirical error in a certain given training set S. The function is from some function space, could be the space of all possible functions, in which case I tell you it will not work, but we'll see that. As an example, if my loss is the square loss, and H would be the space of linear function in X, one variable only, this stupid example, then this empirical risk minimization algorithm corresponds to linear regression, finding the lines that best approximates a set of data in the least square sense. Okay, so we would like to find conditions on H such that the solution of this minimization problem generalizes and is stable. Let me give you some example. For instance, again, these are data. These are pairs of X, one variable only, and Y. And I have 5, 6, 7 points. And I want to find the function. Suppose this is the true one, which I don't know. But depending on which hypothesis space I have, minimizing the error on the data may give me this solution, for instance, which is, of course, different from the true one. And so I'd like to find under which conditions on the space of function H I will get something closer to the true solution. That's the problem of generalization. The stability one, here are some other points, and I can try to fit them through a polynomial. My goodness. You don't see anything. I can tell you, if you see the original slides, that there is something going wildly across the screen, a curve, and it goes exactly through the points. There are 10 points. Can you tell me the degree of the polynomial if it goes exactly through the points?
10?
Yes. Right. This would be, and I can perturb very slightly this point, the original points. They're moved a little bit, and then I'm checking stability, and then I can do the same. Find the best degree 10 polynomial that gives me 0 empirical error, and I find something which is quite different from the other one. So using degree 10 polynomial here gives me a solution which is not stable. Changes a lot if I change the points a little bit. If I use a degree 2 polynomial, it does not fit the data exactly, does not go through the point, but is quite stable. So if I change the points a little bit, it will not change very much. Okay, so showed you, stability, generalization. These are the problems. How can we deal with those? It turns out that you don't need to deal with them independently. It turns out that you can show that stability is equivalent to generalization. The same condition that ensure generalization for ERM ensure stability. Okay? Defined in a certain way, about which Charlie will not speak. No, I want to just wake him up. Good. By the way, the small parenthesis, just increasing, you would expect that the empirical error on this function FSS converges to the expected error. You'd expect that just having infinite data may do this, but that's not true, because for the law of large number to hold, you have to have a fixed function f, which does not depend on the data. Up there, f, this is why I keep the subscript s, depends on s. So you cannot apply the law of large number, this naive intuition that the empirical error converges to the expected error with the data going to infinity is not true. It's true only for algorithms that generalizes, that have this generalization property. Okay. Going back to what I was telling you, there is this result that says that stability defined in a specific way and will deal a lot with stability, a slightly stronger notion of stability in the next few classes. But anyway, stability is sufficient and necessary for generalization. So they're equivalent. You don't need to, unless you are interested in, in understanding the proofs, which are quite complicated. But what is important is that these two conditions that are critical for learning, for practical learning, for practical use of learning algorithms. So you want to have a proxy for predictivity, which is the empirical error, and you want your solution to be stable. If you have one, you have the other. Okay, that's nice to know. And also, it tells you immediately a class of algorithms that you can use to make sure that ERM works, in other words, generalizes and is stable. And the reason is that is well known in physics and mathematics for the last 80 years or so, that the way to make a problem well posed from ill-posed is to use regularization. There is foundational results of Tikhonov and others in the 30s or so that shows that by restricting what I call here the hypothesis space in a certain way, you can make sure that the minimization gives you a well-posed, the minimization process is well-posed, give you a solution that is stable, unique, and that exists. So, there is, for instance, let's see. Yeah. So I mentioned in the first class that if the hypothesis space, or the space of functions, are, say, continuous functions, then you don't have generalization or stability. You don't have this guarantee. Seems it's already quite a restriction. First of all, let's see. I imagine all of you know what a space of continuous function is, but continuity is that for any epsilon exists a delta such that if I choose x prime minus x less than delta, then f of x minus f of x prime is less than epsilon. Okay? That's definition of continuity of f. Now, suppose I have a space of functions, h, that are continuous. They're also bounded. So bounded means that all of f in h, f and all of x in the domain are less than m, some quantity. So that's bounded. And h is equicontinuous if for all f, so let's see, for x prime x2 less than delta, and this could be any x prime x2, for all of this, I have f of x prime minus f2 prime less than epsilon for all f in H. This is equicontinuity. This means for a particular f and a particular x, I can find this give me an epsilon, I find a delta that satisfies this. But delta will depend on f and possibly x. Here, equicontinuous means that for all the function in the space, I can find a universal delta that gives me this property. So in a sense, this says that the function in this space that is equicontinuous have the same degree of smoothness. They cannot change more than something. And this more than something is common to all the function in that H. Okay, that's a subtle distinction, but it makes an important, there is a theorem called D'Arzela theorem that says that if H is bounded and equicontinuous, then it's compact. And turns out that compactness was shown by Tikhonov to be sufficient for regularization, to guarantee a well-posed solution. Okay. So I'm making this example because this seems a subtle distinction, but it makes all the difference for having a class of algorithms that generalizes versus one that does not. Okay? It also makes a connection with things that we see quite often, which is that in regularization, the constraint on the space H is essentially a constraint of smoothness. Your space of functions, in order to be good for learning, have to have some degree of smoothness. Okay? Okay, so, oops, did I lose again? Oh, no, it's here.
Back again?
So, there are two basic old approaches from the 30s to regularization. There are this general theorem, for instance, say compactness is enough. But one way to do it in practice is what is called Ivanov regularization, which in our case is saying I'm minimizing the empirical error, but satisfying a constraint. For instance, a constraint on the F. They have to be, this constraint must be less than some constant. This could be, for instance, that the norm of the F defined in a certain way, will go about, has to be smaller than A, some number. For instance, one constraint could be, let's take the example of a one-dimensional function, could be that the first derivative of x, so df dx, the norm of this must be smaller than A. Okay? This is effectively a smoothness condition. I don't want the changes in the first derivative to be too large. So these are one approach. This is like saying I'm restricting my hypothesis space to be a ball in a space, say, of continuous function. The one which we'll use more often is what is called Tikhonov generalization, which you can look as the Lagrange multiplier version of Ivanov. How do I, if I have a minimization problem, I'm minimizing this quantity subject to this constraint. One way to solve it through Lagrange multiplier is to add the constraint with a lambda to the previous one and minimize the whole thing, right? So Tikhonov regularization is not really a Lagrange multiplier. Is a bit more subtle, but for the purpose of this class, this is the way to understand it. The connection between the two are very close. If you find a solution to one, you can write the solution to the other one. So this is kind of repeating what I just said about this kind of regularization, ensuring stability and generalization. And it what we'll use in function spaces which are called reproducing kernel Hilbert spaces. You hear quite a bit about it. In a sense, I'm telling you this in an informal way, but reproducing kernel Hilbert spaces emerges almost directly from one very basic requirement you want on the functions. You want the functions to be defined at points. It means that for any x, I want to have f of x having a value. Okay? Seems to me a very basic requirement for learning. If you have that requirement plus a couple of other weaker things, then the spaces of function are reproducing Kernel spaces. So this is just to say that this concept you are going to deal with, reproducing Kernel spaces, regularization, Tikhonov type regularization, really follow from basic requirements and properties of the learning problem. You know, just a couple of general comments, but the remarks on what I said is, I think all of the learning algorithm you'll see, well, not all, but most, will depend on optimization. They are learning algorithms are basically optimization under constraints. And the constraints are, for instance, in our case, the key for prediction. The appropriate constraint, like going to continuity, to boundedness and equicontinuity, is the key to make a problem an approach that is predictive. Regularization ensures you this correct type of constraints for learning. It also ensures that the problem, the optimization problem, is well posed, has a unique solution. The solution is stable. So other desirable properties. So we have another 15 minutes at least, right? So I want, as I said, I'll not go through details of regularization algorithms because you will see them, but I want to instead tell you something about sample and approximation error. Okay, so this class is difficult in part because we speak about different kinds of errors, and it's difficult to keep them apart, you know, the first time especially. I spoke about empirical error, generalization error. But now we speak also about sample and approximation error. And probably this is the only time you will hear this in the whole course. It's kind of important, the background to keep in mind. The least important concept is this one of a target space. So a target space is the space of function that is assumed to contain the true function that you are trying to approximate. So the true function is there. And so, in principle, t should be as large as possible. For instance, all square integrable functions, or all continuous function, or all differentiable function. So now these are definitions. Some of them we have seen. The generalization error is this difference between the empirical error and the expected error. But now we define this other quantity called sample error, which is the difference between the expected error and the function that we actually find in H. Now we will not find in general the best function because we have only a finite training set. So this is called sample error. This error will go to 0 if my training set goes to infinity. So this error depends on the fact that the training set is finite. In fact, consistency, which I kind of skipped before, I said is not very interesting, but is what classical statisticians worry a lot about, is exactly this. These are algorithms. An algorithm is consistent if this error goes to 0 for n going to infinity, n being the size of the training set. Now, as we saw, in classical learning theory, the important quantity is generalization, because this tells me that a training error is a good proxy for what I'll do in the future. But another goal is bounds on the sample errors. In other words, determining how quickly the sample error goes to 0 for n going to infinity. Okay? This will tell me how big my training set has to be if I want to do as well as I can. Now, the important thing is that the sample error is kind of intuitive. Goes to 0 more quickly if your model is simple. The intuition is, suppose you have a parametric model with a few parameters. Then the more you have data, the more you should be able to fit this model. After a while, increasing the number of data does not really help. But suppose instead you have a model with 1 billion parameters. It will take a long time before you have enough sampling data to fit the parameters. So typically, the sample error will become, it's smaller, it's better behaved for simple H. Okay, now a new character, the approximation error. This is the one who will not speak at all in the rest of the class, is the error between the best function I can find, the best function in H, and the best function that can happen in the target space. We'll not speak about it because often we'll assume the space of function that we work with, our H, is large enough that we can assume that a true function is in it, so that H is equal T. But in principle, if H is very simple, suppose H is the space of linear functions, then it's very unlikely the true solution will be a linear function, and I deal with an approximation error. And there are reasons to try to use the simplest H I can, because, as I said, if I keep H simple, my convergence will be faster. I will need smaller training sets. So there is a reason for keeping H simple, and therefore for the approximation error to be non-zero. So, if H becomes more complicated, the approximation error, of course, has become small, 0. So the approximation error and the sample error behave in different ways. Okay, the approximation error decreases with age becoming more complicated. The sample error increases with age becoming more complicated. So now something to keep in mind, we can speak about the true error, which is the expected error minus the best I can do. So f0 is a function, it is the true function. I can write it as a sum of sample error and approximation error if I want. And this also shows there can be a trade-off between this, the one I described, between approximation error and sample error. And so this is why given you can look at it from different points of view, but given a training set of size n, there is a best complexity of H for which the combination of sample error and approximation error is minimum, since one increases and the other decreases with complexity. And this is stated here. This is what, again, I mentioned this in case you look at some of the papers and books that are in our references, like Vapnik's book on learning. This is the problem of structural risk minimization, of finding essentially the best H for a given size of training set N. So this is, in regularization, this means you have this lambda, you know, the Lagrange multiplier, is find the optimal lambda for a given training set. So the best combination between the error on the training set and the constraint. Okay. So that's, again, to remind we'll continue to speak about generalization error. We'll speak very little or not at all in future classes about the approximation error. We'll speak about the sample error. Questions? Yeah.
Could you comment briefly on the relationship, if any, between regularization and the techniques used in calculus variations? Are those useful at all?
You know, there are some results in there are some proofs that we'll see related to the subject of regularization that use calculus of variation. There are also some ways around it, but that's kind of the relation. Yeah. Then we'll see. We'll see. In principle, in regularization, the optimization problem is to find the function. So calculus of variation will come in. There is a basic theorem called the representer theorem that essentially tells you that every solution is parameterized in a certain way. So at that point, this classical regularization problem become a normal optimization on a parameters, not on function. So, work. Yeah.
Looks like the generalization error here is active.
Is what?
Active because you are subtracting the test set error from the training set. Is IS the error?
Oh, yeah. No, I think is the projector. This is a plus. Is that you mean?
I mean the generalization error. This looks like the error on the training set minus error.
Oh yeah, you mean here is not. Wait a second. This should be the sample error plus the approximation error, right? So what are you saying?
I was wondering, is the generalization error, you should switch the two errors in the first line, the generalization error.
Yeah.
Because
The generalization error, what?
of
The verb is
I is IS minus I.
fs.
Yes. Should it be I minus IS?
Oh, I see. We usually consider the absolute value of it anyway. So, yeah. Yeah.
Even on regularization, how
Yeah.
do you decide what A is?
The lambda or?
So you want the constraint R of F is less than or equal to A, or how do you decide what A is?
Oh, this is an example of structural risk minimization. You should adjust the A depending on the size of your training set. Okay, so in practice, what you do is what is called cross-validation. So you are on some data that you have kept apart. There are various forms of cross-validation, one leave out, whatever, and you look for the best A or lambda in the case of Tikhonov. Sorry? Like a search or an optimization in itself, yeah. Now, in principle, you could do that in theory because there are some approaches to find the best value given the size of your training set. But the bounds, for instance, in the book by Vapnik, you see how this could be done in principle. It's not used very much because the bounds that you use are very loose, so they don't work so well. So in practice, cross-validation is used. Any other questions? Okay. You see you on Wednesday, math camp.